Hello everybody and welcome to a new problem of the strings chapter. We are given a string and we have to find the length of the longest substring without repeating characters. In this example, we have this string ABCABCBB and the answer is 3. Why is that? Because we have a couple of substrings of length 3 which contain different characters. We have the first one, ABC, we have BCA, we have CAB, we have again ABC, and that's it. If you try all the substrings of length 4, you will see that all of them have at least 2 characters which are equal. Let's start as usual by coming up with a brute force approach. This is simple. We have to find out the longest substring which has some property. So of course we are going to try out each and every substring. We are going to see if that substring has the following property, and if so, we are going to update our answer with its length if it is longer than the previous found one. So just the usual stuff. In order to try out each and every substring, we are going to use 2 nested for loops. We will set the starting index, which is I, in the range from 0 to n-1, where n is the length of our string. And then we are going to set the ending index, which is j, in the range I and n-1. Then we are going to check if the substring s from I to j indeed has no repeating characters. And we are going to write a function for this. And if so, we will update our answer with the length of this string if it is longer than the previously found one. So the code will look like this. As you can see, we need a variable for our answer, which is initially 0 because we haven't found any substring yet. We are going to return the answer in the end. And now all we need to do is think about how to implement this function. There are a couple of ways of doing this. The slowest one is to check each and every 2 characters from the string. And once we find 2 that are equal, we are going to return false. Of course, in the end, if we haven't found any, we are going to return true. So we will need 2 nested for loops, one for setting the index of the first character, the second one for setting the index of the second character. Then we are going to check if they are equal. If so, return true, else return false. So I'm not going to write the code for this. It's super simple. But as I said, it is slow because it makes this checking in big O of the length of the substring that we are going to check squared. Let's do something faster. If we are going to have at least 2 equal characters, this means that there will be some letter from A to Z which appears at least twice. So what we can do is actually count for how many times each letter in the alphabet appears in the substring, and then check if there is at least 1 letter with the frequency greater than 1. And this is how the function will look like. It has only 1 argument, and we will check if the string S consists only of different characters. To count the number of occurrences, I'm going to use a frequency array. There's no need in using a hash table because all we want is count for how many times each letter in the alphabet appears. And as you know, there are 26 letters in the alphabet. So yeah, we can definitely store an array with 26 elements. So initially, each and every frequency is going to be 0. And what I'm going to do is iterate through each character in my string. Then I'm going to increment the number of occurrences. As you can see, I do C minus A. So I make sure that I take the SG code and just point it to a number from 0 to 25. I increment it by 1. And now, if the number of occurrences of this character is greater than 1, so I have encountered at least once in the past this character, I'm going to return false. In the end, I'm going to return true. And this is how the brute force approach looks like. Let's analyze the time complexity. In the main algorithm, we have here a constant operation, which is executed only once. Constant operation executed only once. We don't care about this. 2 nested for loops. Then we have this check, which calls the function. So I need to analyze the time complexity of the function first. And then, of course, we have this one, which is a constant. So in the function, let's see what happens. First of all, I just build an array of 26 elements, right? So I can say this makes a total of 26 iterations. I can say big O of 1 because 26 is a constant. But now we know that there is that notation sigma, which means the size of the alphabet. So I can say that this is big O of sigma. This looks way prettier and it's more professional. Then I take each character in S. This incrementation, of course, is constant. Checking is constant. And the returns are also constant. So what happens here is that I do this for a total of the size of the string S times. So this will be big O of the size of the string. Let's say s.size or s.length, right? Cool. So each time I call this function, I have big O of the length of that substring. And because we know I and j, we know that this is going to be the length j minus I plus 1. So the number of operations that are executed here depends on the value of I and j. The value of j is in this for loop, so it will depend on the for loop, and then the value of I and all the values that j are going to take also depend on this for loop. Now, we know what you have to do in theory. Take each value of I and j and write on paper each of these numbers, add them together, and try to find the value for that sum. But we have already tried doing that, and we got an ugly sum which couldn't be computed. So in this type of scenarios, we can say that this is at most n. This makes at most n iterations, right? From I to n minus 1. And this one, of course, makes not even at most, but also n iterations. So we multiply this together, and we get that the time complexity of this brute force approach is big O of n cubed. Now, of course, we've got a lot of experience, and we can tell that this time complexity is due to the first stage, which is checking each and every subarray, and the second stage, which is checking if that subarray has some specific property, or actually computing some information for that subarray. We have solved a couple of problems with brute force approaches similar to this one, so we know what needs to be done. We know that we should use the fact that we compute some information for each and every substring. So maybe I can optimize this second stage and make it constant if I use the fact that whenever I want to compute some information for the subarray ij, and that information is of course number of occurrences, we know that we have already computed this information for the previous subarray. So most of the times the previous subarray will look like this, I and j minus 1, right? And we know the information for this subarray, and now we want to compute number of occurrences for the current one, which is ij. So of course, the only difference between these two is that we have just added a new element. So instead of resetting the number of occurrences frequency array and counting again for how many times each character appears in the substring, all we have to do is just increment the frequency of the new character. And of course, check if that frequency is greater than 1, that means the character already appears, so the substring is bad. Of course, if this substring ij is bad, each and every next substring which has a greater endpoint is going to be bad. So we just make the incrementation, which is constant. We check this, which is also constant. If this happens, we can break because this substring and also the next ones are going to be bad. If not, we are going to continue and compute the information for I and j plus 1 and so on and so forth. So this transition is actually very smooth and it can be performed in constant time. Now, of course, we have the second type of transition when j will not get incremented because j actually has the value of the last index in the string. So our previous subarray looked like this. It was I minus 1 and n minus 1. And now, of course, the current subarray, which we want the information for, is going to be I. And what's the first value for the j when we start with a new I? Of course, it is also I. So what needs to be done here is, first of all, reset our number of occurrences frequency array because it contains the information for this substring and we don't have these characters anymore. So just set it again to 0, 0, 0 for 26 times. Then we will just increment the number of occurrences for the one and only character, which is s of I. Of course, we won't have any equal characters as it is only one, so no need to check this. So this transition is going to be executed in big O of sigma, because of course we either reset the frequency array or we build a new one, doesn't matter. There are 26 elements here. Of course, the beautiful part about this is that this transition is going to happen exactly n times, because there are n times where we try out a new value of I. And of course, this transition is going to happen most often and is going to happen for the rest of the times, which is n squared minus n. So we still have a big O of n squared from here and the big O of n cross sigma from here. And because sigma is way less than n, the final time complexity of our next brute force approach is going to be actually big O of n squared. Let's take a look at the code. This is how the code looks like. As you can see, answer equals 0 initially. I try out each and every starting index. I have the second type of transition. So I build another array or I reset the initial one, doesn't matter. Then I try out each and every end index. I increment the number of occurrences of the new character. And if the number of occurrences is now greater than 1, I break because I know this and all the next subarrays are not going to be valid. And of course, if not, and I'm here, I update the answer, and in the end, I just return the answer. Now, again, we have some experience. We have seen some brute force approaches like this, and we know that when we have something like this, we find the first J, which is a bad one, and all of the next ones are going to be also bad ones. This is a very, very good signal for a two-pointers technique. And indeed, what we do in this algorithm is that for each value of I, we compute the greatest value of J such that the substring S from I to J is still a valid one. So the only property that we need to make sure is satisfied in order to be able to proceed with a two-pointers technique approach is check that max J of I is always less than or equal to max J of I plus 1. If this happens, we know what needs to be done. Whenever we transition and try a new value of I, we are going to keep J in the same spot and just try to increment it as much as we can. This is actually very simple to check. If, let's say, this is the value of I, the pointer is here, and we have some new characters, some characters, and somewhere here, let's say we have max J of I, right? So this is the longest substring which starts on position I and has only different characters. When we move to I plus 1, so here we have I plus 1, of course, because this one is a substring of the previous one, this one is also going to be valid. There are only going to be different characters in the substring. So this is also a valid J for I plus 1. Of course, it could be even greater. Maybe the max J of I plus 1 is here or here, who knows? But we know it is at least equal to max J of I. So our property is satisfied and we can proceed with the two-pointers approach. So all we need to do is see how to make this transition. Well, it is, of course, very simple. What happens is that, let's say this was my previous I. We have finished finding the greatest J. And of course, in number of occurrences, we have the frequency of these characters. Now, because we move to the next I, first of all, I'm going to decrement the frequency of this character because it's not part of our substring anymore. And then I'm going to increment J as much as I can. How do I do this? I will check if number of occurrences of this character is already greater than 0. And if so, of course, I can't push this character into my current substring and I stop. If not, it means everything is fine. So I will extend my substring and increment J and of course increment its number of occurrences and continue trying out the next J's. Let's see how the code looks like. Cool. And this is how the code looks like. As you can see, my array number of occurrences will now be named isPresent and is going to be an array of booleans. Why is that? Because now I make sure that in my current substring, each character appears at most once. So the only information that I need is that character already present or not? So I will initialize this array with 26 values of false. And what I'm going to do first, like we always do in the two-pointers technique, is compute by hand the value of max J of 0. So I try out each and every character starting from 0. And what I check is whether that character is already present in my current substring. And if so, that means I'm going to stop. I can't take this character. So I will break. Otherwise, I will set it as true and continue looking for greater J's. When we exit this for loop, we can do this in one of two ways. The first one is through the break. So whether we have encountered a character which is indeed a bad one, which means that this J is not a valid one. So I'm going to have to, of course, decrement it at the end. Or we either exit the for loop naturally when J becomes N, which also means I should decrement it because N is not a valid index. So in the end, I will decrement the value of J. The isPresent array is indeed going to be the right one because I make sure that only if that J is valid, I'm going to set it as true, which is cool. The answer is going to be initially equal to J plus 1 because that's the length of the substring that starts on position 0 and ends on position J. And then I try out each and every other start index from 1 to n minus 1. What do I do first? Because now I've basically removed the previous character from the current substring. I'm going to set isPresent of the previous character to be equal to false. And then, of course, I increment J for as much as I can. So first of all, if J is less than n minus 1, so J plus 1 is a valid position, and that character is not already present in my substring, so isPresent of that value equals false, then I can increment J. I should take this character into my substring, so I set its isPresent value to be equal to true, and then because I know J is a valid one, I update the answer, which in the end I will return. Awesome. What's the time complexity of this approach? Well, here, of course, we have big O of sigma. Then we make this for loop. We check this, which is constant. The break is constant. We set this, which is constant. So here we do at most n iterations. So we can say this piece of code is big O of n. Then constant here, constant here. We make at most n iterations here, but let's continue. This is also constant. We have this while loop. Let's continue. Constant here, constant here, constant here, and constant here. And of course, there are two nested for loops, but we have the two pointers technique. We know that I is only going to be incremented for at most n times, right? And j is only going to be incremented for at most n times. So all of the constant operations here will happen for at most n times, which makes this piece of code big O of n. And this is, guys, an algorithm that has a final time complexity of big O of n plus sigma, theoretically. And you can do that, and there's nothing wrong with that. But you can even say big O of n because it is way more important than the sigma. When you have big O of n crossed sigma, yes, then you definitely should take it into the time complexity because they get multiplied and this is a significant factor. But when you have big O of n plus sigma, I mean, both of them are correct. You can say big O of n and it will be definitely good. And then, of course, the memory time complexity is big O of sigma as we only use this extra array. And what I will show you next is another solution which I find prettier. And the beautiful thing is that you don't need to have been through the Algo Academy mentoring program to come up with that solution. You don't need to know the two pointers technique. You just gotta be creative. So I'll see you on the next one.